Have you ever wondered how math, which you might have hated throughout high school, came into existence? I'm sure you haven't.
No.
Perhaps in the minds of many of us, it remains a pile of frustrating equations waiting to be solved or complex formulas that need to be memorized.
A lot of boring math later.
Nevertheless, I will still take 8 minutes to explain the origins and development of the language that forms the foundation of all science and technology, the underlying structure of the universe, mathematics. The story of mathematics begins around 30,000 BC with the rise of human consciousness. The first and most basic need was counting. To survive, early humans had to track their prey, their herds, the seasons, and the days. This enabled them to predict the future and manage resources. Primitive people used the method of one-to-one correspondence, a stone, a notch, or a finger for every animal in a herd. Yes, they used mathematics for survival in its purest and most practical form. During this period, mathematics was less a mental tool and more a physical tracking system. Among the oldest concrete evidence from this era are notched bones found in Africa and Europe. For example, the organized markings on the approximately 40,000-year-old Lubombo bone, South Africa, and the 20,000-year-old Ishango bone, Congo, suggest that people were not only counting but also organizing those counts, perhaps engaging in groupings that resembled simple addition and multiplication. The groupings on the Ishango bone have even been linked to prime numbers, suggesting that the people of that time had a more sophisticated knowledge of rhythmic counting than we might assume. However, the biggest deficit in mathematics during this period was the absence of zero. Number concepts were strictly tied to concrete objects. The abstraction of nothingness, or the empty set, had not yet arrived. This limited mathematics. For a civilization to advance, abstract thought had to surpass concrete calculation. With the development of record-keeping skills, the need to represent larger and more complex numbers would arise. By the 4th millennium BC, the rise of complex civilizations in Mesopotamia and Egypt fundamentally changed the need for mathematics. They were no longer just counting sheep. They were using mathematics in state administration, tax collection, calendar creation, and colossal architectural projects. The Egyptians made particular progress in the field of geometry. The annual flooding of the Nile River necessitated accurately recalculating and redrawing the boundaries of agricultural land, requiring precise calculation of right angles and surface areas. Special artisans called rope stretchers, harpanodaptai, divided the land using simple yet effective geometric methods, such as the 3-4-5 triangle. The Rind papyrus and the Moscow papyrus show that the Egyptians possessed practical knowledge regarding fractions, area calculations, and even how to calculate the volume of a truncated pyramid.
What?
The approximate value of P used by the Egyptians was quite accurate, and these methods, developed through trial and error, made the construction of the Great Pyramids possible. Yet, Egyptian mathematics focused more on how than why.
Why?
They did not feel the need to prove their methods. The biggest breakthrough in the history of mathematics came from the Mesopotamian civilizations that developed between the Tigris and Euphrates rivers. The Babylonians began to view mathematics not only as a practical tool, but also as a theoretical discipline, integrating it with astronomy. The Babylonians developed the sexagesimal system. This base 60 system, which we still use today for hours, minutes, and angle measurements, meant that the value of each digit depended on its position. This was revolutionary. They could now represent an infinite number of quantities by changing the position of the same symbols without having to memorize hundreds of different symbols. The Plimpton 322 tablet is the most striking evidence of how advanced Babylonian mathematics was. Dating back to around 1800 BC, this tablet contains a systematic list of Pythagorean triples. This shows that the Babylonians knew the basic principles of geometry, number theory, and trigonometry 1,000 years before Pythagoras. However, Babylonian mathematics also had a flaw. Despite using a positional system, they did not use a definite symbol for zero in the place values. The third evolutionary leap in mathematics took place in ancient Greece. While previous civilizations based mathematics on practical calculation, the Greeks founded mathematics on the question of why. They moved beyond calculation and felt the need to prove knowledge. Thales of Miletus is credited with being the first to introduce deductive proof to mathematics. He showed that a theorem could be proven not by empirical observation, but by a chain of logic. Pythagoras' most famous discovery was his theorem concerning right triangles and its power to explain the order of the universe. However, the Pythagoreans faced their greatest challenge with the discovery of irrational numbers. This shattered their belief that the entire universe could be explained by whole numbers. This problem also demonstrated the vast potential scope of mathematics. Around 300 BC, in Alexandria, Euclid gathered this scattered Greek knowledge and authored the monumental work, The Elements. He demonstrated how all geometric knowledge could be derived logically. The Elements laid the foundation for the modern model of scientific proof and served as the standard textbook for Western education for thousands of years. Archimedes was a genius in mathematical physics and engineering. He approximated pi to its most accurate value, fractionally, up to that point. While mathematical progress stalled in the Western world with the collapse of the Roman Empire, the mathematical revolution shifted east, particularly to India, and subsequently the Islamic civilization. Beginning in the 5th century AD, Indian mathematicians solved the problem that the Babylonians and Greeks had not: the invention of zero. Mathematicians like Brahmagupta defined zero not just as a placeholder, but as a mathematical entity, a number that could be both added and subtracted. The combination of zero with the Hindu-Arabic numeral system created the modern positional decimal system. This system simplified calculations so fundamentally that it was revolutionary for the future of mathematics and formed the infrastructure for today's finance and commerce. This knowledge later reached its peak during the Islamic Golden Age. Arab mathematicians adopted and developed the Indian system. Al-Khwarizmi, with his work Al-Jabr, the origin of the word algebra, introduced this new system to the West and established algebra as an independent discipline. Algebra is the art of finding the unknown using the known. It laid the foundation for modern equations. Concepts like trigonometry, sine, cosine, and tangent were also developed and disseminated during this period. This knowledge found its way back to Europe through figures like Leonardo Fibonacci during the Middle Ages, setting the stage for the scientific revival of the Renaissance.
More feeling.
The final major leap in mathematics occurred in the 17th century with the independent invention of calculus, differential and integral calculus, by Isaac Newton and Gottfried Wilhelm Leibniz. Calculus is the mathematics of motion and change. It allows us to examine instantaneous rates of change, derivatives, the areas of curves, and accumulated changes, integrals. This tool became the indispensable language for explaining the laws of the physical universe, from gravity to electricity and magnetism. Without calculus, space travel or modern engineering would be unthinkable. The 19th and 20th centuries marked the modern theoretical age of mathematics. Gauss, Riemann, and Lobachevsky invented non-Euclidean geometries by rejecting Euclid's 2,000-year-old untouchable parallel postulate. Sorry, Euclid. Alan Turing's theoretical work laid the foundation for modern computer science. Every digital device we use today is based on mathematical logic derived from the Babylonian positional system, the Indian zero, and Newton's calculus. Mathematics, starting from those first notched bones built with abstract proofs, algebra, and infinitesimals, is a living, continuously evolving language that reflects and explains the universe itself. We are the inheritors who continue to write the most complex sentences in this language. That is why we should not hate it. Thank you for watching. I put a lot of effort into this video. Please subscribe.